So in our last video, we introduced the kinetic theory of gases, and in this video, we're going to use that theoretical framework to describe a series of gas laws related to various changes in pressure, volume, and temperature of a contained gas. To review what the kinetic theory of gases states, it assumes that, or it states that a contained gas is a collection of particles, molecules, or atoms in constant random motion, and that we can describe the macroscopic properties of that gas, things like its temperature, its pressure, its volume, by reference to the motion of the the individual particles. And so we can also describe changes in the gas by reference to those changing particles. And so temperature we described as the average kinetic energy of the particles, or how fast they're moving. Pressure is collisions of the particles with the walls of the container. And volume then is just the free space available for the particles to move about. And so one of the things about the kinetic theory, which is similar for all theories, is that this is not a verifiable thing. The smallest sample of matter, of gas, that you would be able to actually measure a temperature for is going to contain a vast number of particles on the order of moles of particles. And even if you are tenths, hundredths, thousandths of a mole, you're still talking in the neighborhood of 10 to the 20th particles. So you could never actually count them all, measure all their kinetic energies, and take the average. So we're relying on an unverifiable approach, and yet the implications of those approaches and the results that they produce give us pretty good reason to think that this theory is a useful way to describe gases. Let's start with the first relationship, which is the pressure-volume relationship at constant temperature. And this is referred to as Boyle's Law in reference to the physicist and chemist Robert Boyle. Robert Boyle, you may remember from the last video, was well known for having constructed a series of air pumps. And then he would use them. He would go around to various scientific meetings and do demonstrations by evacuating air out of the air pumps. And so the relationship to pressure and volume at constant temperature means that we're going to keep the speed of the particles constant. And we're going to see what happens to the pressure if we change the volume, or the volume if we change the pressure. So here we have a container with a movable lid. And so you might think about the relationship here. If you increase or if you decrease the volume, I should say, from that first picture to that second picture, we've pushed the plunger down. And so now there is much less space for the particles to move around in. And if they're moving at the same speed as they were in picture one, then what do you think would be the relationship with the number of collisions they would have with the walls of the container? So it ought to be fairly obvious that there are going to be more collisions if you have the same number of particles moving at the same speed in a smaller space, and that is the relationship that we find. Pressure is inversely related to the volume. If you drop the volume, you're going to increase the pressure, and vice versa. That's what the inverse relationship is. One goes down, the other has to go up. And the mathematical relationship we get for that is P1 V1 equals P2 V2. So it's a product here, and it should make sense that if we're at constant temperature, then that means the product of pressure and volume has to always equal the same number. So if your P gets bigger from P1 to P2, then V1 to V2 better get smaller if that equal sign is going to stay the same. And again, we refer to this as Boyle's Law. The next relationship to take a look at here is the temperature-volume relationship at constant pressure. And so again, we can think about what's going on here. Constant pressure means same number of collisions with the wall. Well, think about what's going to happen here. If you increase the volume, that means the particles are going to have much further to go from wall to wall. And so if they're going to have the same number of collisions with the bigger container that they had with the smaller container, well, they sure as heck better be moving a whole lot faster. So if the volume goes up, temperature better go up as well, so that you maintain that constant pressure. And so we say that temperature is directly related to volume, right? So increased volume means you have to have increased temperature. Decreased volume means you need to decrease the temperature to keep the number of particle collisions the same. And that direct relationship looks like a product. V1 over T1 equals V2 over T2. And this is referred to as Charles' Law. Charles' Law, named after the French chemist Jacques Charles. Charles was actually a fairly avid hot air balloonist, which is where he got interested in understanding the relationship between volume and temperature of a confined gas. In this case, it would be the combined gas inside a hot air balloon. The third of the relationships, we've kept pressure constant, we've kept temperature constant. Now what we're going to do is keep volume constant and look at the temperature-pressure relationship. So we have an inverse relationship with pressure and volume. We have a direct relationship with temperature and volume. You might take a look at this diagram and think through the process and see if you can determine whether you think that temperature is directly or inversely related to pressure. And maybe you'd pause the video, write something down so that you can check yourself. Okay, so we have in that first container on the left, we have a number of particles moving around in there. If we increase the temperature while keeping the volume constant, particles are going to move faster. So does that mean you're going to get fewer collisions or more collisions with the container? And it should seem obvious that you're going to get more collisions if the particles are moving faster, and so that would be a direct relationship. Temperature goes up, pressure goes up. Direct relationship is going to be a fraction rather than a product. That's P1 B1 or T1 equals P2 T2. This is referred to as Gay-Lussac's law. Gay-Lussac was a French chemist, Joseph Louis Gay-Lussac. One of the things Gay-Lussac is well known for, besides his gas laws, is he, roughly the same time as some other individuals, but he independently discovered the ratio of hydrogen to oxygen in water, that it was a 2-to-1 ratio. And so he kind of has that claim to fame behind him, as well as having this gas law. Okay, so let's look at what happens when you put all of the gas laws together. We have our volume-temperature relationship. This is, of course, at constant pressure. We have our pressure-volume relationship, which is at constant temperature. And we have our pressure-temperature relationship, which is at constant volume. And the question you might ask is, what happens if you're not keeping one of those variables constant? Well, you get what's called the combined gas law. So notice temperature is always on the bottom, pressure and volume are always on the top. So we get P1 V1 over T1 equals P2 V2 over T2. You should probably put that in your notes somewhere, circle it, underline it, stars, arrows, exclamation points. This is a super important equation with respect to the behavior of gases. It lets you know how other variables are going to respond to certain changes in your combined gas. And essentially what we're saying here is that pressure, volume, temperature as a combination of variables will always equal a constant if, and this is the one point we haven't really put out there yet, all of these different gas laws, Charles, Boyles, Gay-Lussac, rely on the fact that you're keeping the number of particles inside that container constant, or the number of moles. Okay, let's look at how the combined gas law works. It's actually fairly simple. So you have a sample of methane gas in a flexible container. That means its volume can increase and decrease. It has a volume of 3.8 liters at -5 degrees Celsius. If the gas is heated to 86 degrees Celsius at constant pressure, what will be the new volume? And so we have P1 V1 over T1 equals P2 V2 over T2. Always start by writing your equation out. Now, here's the thing with a combined gas law. You don't need to know the individual gas laws, Charles, Boyles, Gay-Lussac. If you know the combined gas law, you can always find the others. So we're looking here at a volume-temperature relationship, and here's the really important thing, at constant pressure. And so if pressure is constant, that means P1 and P2 are equal, which means if you divided by that pressure, you would cancel it out of the equation. So you can always arrive at any of the other gas laws by just crossing out the value that is held constant, right? If we want Boyle's Law, that means we're doing it we're going through a process at constant temperature, and the T's would cancel out across the bottom. Here we're canceling out the pressures. Now, once you've done that, and it might be the case that nothing cancels out, you might have to put something in for every value. So go ahead and plug your values in. Of course, our unknown here is going to be V2. We're trying to find the new volume if we change the temperature. Remember, you must have your temperatures in Kelvin whenever dealing with gas laws. The reason for that is fairly simple. Kelvin's absolute zero. If we're talking about motion of particles, 0 Kelvin is when particles stop moving. There is no temperature colder than 0 Kelvin. And so if you're going to relate relationships of pressure, volume, and temperature to the motion of particles, you have to be in an absolute temperature scale. There would be no meaning to negative 16 degrees. That would be moving slower than not moving. So you have to be in absolute temperature scales if you're going to reference particle motion. So we take negative 5.0 degrees Celsius, we add 273.15 K. If you haven't yet written that in your notes, you need to do that. Degrees Celsius plus 273.15 is equal to degrees Kelvin. We're going to need to round that off to the tenths place, but I'm going to go ahead and just underline that right now and wait till the end to round off for significant digits. 3.8 liters on the top. We have then V2 is equal or divided by our new temperature, which is 86 plus 273.15, and that has to be rounded to the ones place. Okay, mathematically, we're going to multiply both sides by the temperature because we want to get that V2 by itself. That cancels out Kelvin on the left side. That cancels out the temperature on the right side. And so you get an expression, 359.15 times 3.8 divided by 268.15. You're going to have two significant digits in your answer. And before you start punching in the calculator, you need to think about the process. We have a direct relationship between volume and temperature. Our temperature went up. Do you expect the volume to go up or down? Hopefully, since it's a direct relationship, you would know in your head that it's supposed to go up. And you need to have that in your brain before you push your calculator numbers in case you accidentally fumble a number. If you get a smaller volume, that should tell you something went wrong. Go back and look at your setup. Go back and make sure you have your temperatures in Kelvin. Go back and make sure that you multiplied when you're supposed to multiply or divide when you're supposed to divide so that you get that reference. And you should end up with about 5.1 liters. And one last point before we wrap this one up, if we had kept that negative 5 degrees Celsius on the left side of the equation, when you did your calculation, you would have ended up with a negative volume, which would mean less than zero space. And of course, that just doesn't make any sense.